first example, we are going to see a steel girder and performing a nonlinear analysis. Well, here is the model. It's just a steel girder with some stiffeners here and a pressure on top. If we analyze the relationship between the loads on top and deflection, it's very clear that if we are solving elastic linear analysis, we will have the relationship between loads and deflections will be aligned. This is straight line and proportional deflections to loads. If we are solving the same model with elastic material, elastic behavior, but taking into account second order effects, loads will be increased and deflection will be increased due to this deformed shape. So we will follow this second line and deflection will be increased due to this geometric nonlinearity. But it's still very far to the real behavior of the structure. If we add nonlinear material behavior, we will start having yielding in the model, so it will reduce stiffness and the deflection will be increased. So we will have this other line here with rigid plasticity. And if we put them all together, nonlinear geometric nonlinearity or geometry and material behavior, we will have these two lines. Some softwares analyze this material nonlinearity, this yielding, generating plastic hints. Those plastic hints, when in those nodes forces or stresses goes over a limit, the condition of those nodes, that decrease of freedom there is released, and we will have some plastic hints. So we will have an approach of multilinear curve. But if we have distributed plasticity, that is plasticity in the elements along all the whole member, we will have this last curve. So we can see result is very different from solving in elastic linear analysis or solving with a real simulation taking into account all nonlinearities. CivilFEM is a very easy to use software that includes all these nonlinearities, and we can obtain the real behavior of the structure taking into account the second order effects and distributed plasticity. Let's load this example to understand better this behavior. So, here we have the bin, distributed load. Here we can see the load, the mass, the pressure, boundary conditions, and we have solved it in linear elastic way, and we can see the results. The load I'm applying here in the model here I have the load in the model is 2.5 tons meter over this line. So if we plot vertical displacement, that is set displacement. Here I'm going to reset the scale. Here is the vertical displacement I'm getting. If I try to check if I'm having any type of buckling, I cannot see any type of buckling. Only vertical displacement to vertical loads, no lateral displacement, no lateral component. So I cannot see how this model will the buckling shape of my model and the results I will get. But codes and standards give me the possibility to check this model to obtain the strength using some formulation, the strength of this column, of this beam, and compare with the forces and moments I get. So if I perform bending buckling analysis and click OK, I will get those results. If I load the results, I'm not checking again. I've already solved all the models, but I'm plotting the results. Here, checking results. This one. Here. Okay. So first result I'm going to get is the total criterion, which is a sort of safety factor. Total criterion, we can see here in the center, is 0.97. This is the ratio demand capacity. It means capacity is a little bit greater than demand. So this model is okay, but almost in the limit. Okay. So also I can see here some other results. Section class. The section class is used by codes to analyze the possibility of local buckling in the plates. American codes define the section class as compact, non-compact, and slender. So slender sections is where local buckling is likely to occur, and in those points the software reduce and the codes reduce the capacity to take into account those plate backlings. So in my model, if I run from 4 to 1, the section class, if I plot, the section class is 4. Section class 4 is slender. In the Eurocode 3, we have section class 1, 2, 3, and 4, from compact to slender. Okay, this is the results we can get. Not much information. I don't know how it's going to, how will I have some buckling effects and anything else. So the next step I can do is to perform a linear buckling analysis. The material will be linear, so I will have nonlinear geometric behavior. In this case, is this model. I've performed a linear buckling analysis. In order to perform the linear buckling analysis, I have to indicate the buckling modes I would like to extract. They are extracted here with the number of modes, 20 modes. I'll extract them and I can see results I get. I'm going to start with the first buckling mode. Okay, I'm going to plot horizontal displacement and to see how these buckling modes are with the deformed shape, and plot again. Well, here I can see the first buckling mode is a lateral buckling. If I get the information of the extracted modes, I can see here the buckling modes and the buckling load coefficient. It means I applied 2.5 tons meter length over my model. So it means this buckling mode happens for 1.327 times the load I have, and the same for the rest of the buckling modes. If I get some of these values negative, it means loads should be applied in the opposite direction for having buckling results. So I will see the other buckling shapes I can have in my model. Well, the next one is local buckling of my plates. So I know that to avoid this buckling mode, I need to place some stiffeners here. Okay, I can see here in a better way. I advance the different plots. Well, this is like a combination of lateral buckling plus local buckling of the plates, other way to for buckling of buckling of the plates on both sides by close to the supports.
Yeah. Well, at the end is a eigenvalue analysis, so we'll all the buckling modes we will have the shape of our buckling shapes.
Different buckling shapes with different buckling in different parts of the model. Okay, so this is the geometric nonlinearity, but non-material. We are using linear material behavior. If we would like to use both together, we are going to move to the next example. In this example, I've added material nonlinearity. Here you can see the analysis type I'm using this table with these values. If I plot the graph, well, this is the stress-strain relationship that I will have in my material. I also need to take into account second-order effects. So here, when solving configuration, I have to click here to take into account second-order effects, large deflections. So with the model, now I'm applying here the load and can solve the model. In order to analyze the model behavior over the design loads, I'm going to apply double value of my overloads. Instead of 2.5 tons per linear meter, I'm going to apply 5 tons per linear meter. So well, I'm going to solve the model, and I'm going to divide the model in 100 steps to divide the solution. If the model collapses, the software will not find the solution and stop solving. So I can analyze the maximum load of my model, taking into account the percent of the load the software was able to solve. If I divided my load in 100 steps and the solution stops in step number 80, it will mean the maximum load, the ultimate load, is 80%. Well, after defining these steps, I should press start and solve the model. I don't want to spend a lot of time solving the model, so I've already done and can plot results. To plot results, in the next tab, load file, I'm going to check first mode. Okay, no, sorry. Well, but it's very important for this sort of models that buckling should happen. So loads should be applied with a eccentricity, small eccentricity, to produce the buckling modes I would like to analyze. I can introduce that eccentricity in many ways, but well, the best way to add this eccentricity is to use the linear buckling modes, to use the deformed shape of the linear buckling modes, scaling a small size, so I will have a small eccentricity, and I can reproduce those different buckling modes. So the way to introduce that deformed shape is here, mesh, deformed shape. If I click here, I'm going to introduce a small deformed shape in my mesh. The deformed shape will be similar to my buckling mode. So clicking here, I can select the first buckling mode, open, and I can scale this buckling mode to a maximum displacement value or scale that result. I don't know the values of that buckling mode, the maximum values I have, so I'm going to scale to a maximum displacement. I click here, and I can scale it to, an example, 1 inch. 1 inch will be my eccentricity. If I click here, okay, I will have that eccentricity applied to the model. Here I can see that I have a small displacement here. So due to this eccentricity, geometric nonlinearities will be taken into account, and on the deformed shape will increase forces and moments. If I get my results after applying this, I solve the model and get my results here, and these are all the results I got. I can see the model stop in the step 54. It means it solved 54% of my load. I'm going to load the last result and plot the format shape in the normal direction. Okay, these are my results. I'm going to scale it a little bit. It was too scaled. And here is my deformed shape in the backlit mode. I'm going to reduce a little bit the scale. Well, here I can see better the real backlit of my structure. It's not the first backlit mode. It's like a combination of lateral backlit plus local backlit on these points. Both are happening almost at the same time. I'm going to plot yielding in my model. Equivalent plastic strain. I can see I'm having yielding here in these points, in the flank, also here in the wave. To be able to see better these results, I'm going to modify the scale. 0 and plot again. So I can appreciate better yielding points in my model. I'm going to go back in the steps where load was applied to see where yielding start. Here I can see that when I have 54% of my load applied on the model, I have yielding. If I go back, yielding is reduced. Almost inappreciated yielding here. And I can see when I have the 43% of my load, I had no yielding, but in the next step with the 44, it starts yielding. So I can analyze much more details of my model with the nonlinear analysis. Also, I can plot the variation of displacement versus load. In this model, if I get the node number here, in example, this 513, if I plot displacement y direction of that node, 512 in example, plus, okay, I can see the capacity curve of my structure. At the beginning has a linear behavior, and when I get about 44% of the load, plasticity starts, yielding starts, and collapse happens with 54%. Well, if I compare those results together, I can see here two backlit modes, the capacity curve of the structure for lateral backlit, and with code checking I applied 2.5 tones per linear meter. The safety factor was, well, the demand capacity ratio was 0.972, so the invert is the safety factor. The capacity using the code checking is 2.27. For the linear backlit, I obtained these backlit factors for the same load, 2.5, so the load is higher. The capacity is higher. The nonlinear analysis, the ultimate load, as I saw, is 54% of the load. I applied 5 tones higher load to obtain all this curve until collapse happens. And I know my ultimate load that produce collapse is 2.75. And I know that my first yielding happens with the 43% of the load, that is 2.15. I can see, if I compare these results, that code checking is very conservative, so code checking could lead me to over-design structures, and I also don't have much information about what is happening. With the linear backlink, I have some backlink modes. I will know how the deformed shape will be. But if I perform a real nonlinear backlink analysis, I have the elastic limit of the structure, the ultimate load, if this structure is ductile or not, if I have post-backlink stiffness, and have much more information about my model. So I can improve my designs because I know where to apply here, where to define stiffeners, where to apply some constraints, some bracings to make my structure much more ductile and finally much more safe.